Hello everyone. I am Teacher Chen from the Electronic Information Engineering Teaching and Research section of Wuzhou University, and welcome you to this mini lecture. Today we will study section 7.5 in chapter 7 on complex frequency domain analysis of systems, the system function and system characteristics of discrete time LTI systems. Next, we will learn this section's content through the following aspects. First, let us talk about the definition of the system function. Under zero-state conditions, the ratio of the z-transform of the system output, yf of z, to the z-transform of the input f of z, is denoted h of z, and is generally called the system function of the system. In a linear time-invariant system, assuming the initial state is 0, the system's response to a unit impulse sequence input is called the unit impulse response h of k, which reflects the system's characteristics. Taking the z-transform of h of k gives h of z, which represents the system's complex frequency domain characteristics. Therefore, we can use the system function h of z to solve the zero-state response of a discrete time system. The steps are as follows. Firstly, compute the z-transform f of z of the system input f of k. Secondly, from the unit impulse response h of k, compute the system function h of z in the z-domain. Thirdly, compute the z-transform of the system's zero-state response. Finally, take the inverse z-transform of yf of z to obtain the time domain zero-state response yf of k. Example 1. For a certain linear time-invariant discrete time system, when the input is f1 of k equals u of k, the zero-state response is y1 of k equals 2 to the power k times u of k. Find the zero-state response, y2 of k, when the input is f2 of k equals k plus 1 times u of k. Step 1. Compute the z-transforms and regions of convergence for the system inputs f1 of k and f2 of k, as well as for the zero-state response y1 of k. Step 2. Since the system function h of z is equal to the ratio of the z-transform of the zero-state response y1 of z to the z-transform of the input f1 of z, simplify this ratio to obtain h of z. Step 3. Because the z-transform of the zero-state response y2 of z is equal to the product of the z-transform of the input f2 of z and the system function h of z, simplify this product to obtain y2 of z, and then expand it into partial fractions. Step 4. Take the inverse z-transform of y2 of z to obtain the time domain expression y2 of k for the system's zero-state response when the input is f2 of k. In the above formulas, a numerator factor, 1 minus c sub r times c to the power of negative 1, produces a 0 of h of z at z equals c sub r and a pole at z equals 0. A denominator factor, 1 minus p sub k times c to the power of negative 1, produces a pole of h of z at z equals p sub k and a 0 at z equals 0. The poles z equals p sub k and zeros z equals z sub r of h of z can be real, imaginary, or complex. Since the coefficients a sub k and b sub r are real, if a pole or 0 is imaginary or complex, it must appear in a complex conjugate pair. Apart from the constant g, the system function is completely determined by its poles and zeros. Therefore, the pole, 0 distribution of the system and its region of convergence determine the system's characteristics. The pole, 0 distribution of a discrete time system is shown in the figure, where numbers in parentheses indicate the multiplicity of a 0 or pole. In addition, the pole, 0 distribution of a discrete time system corresponds to its time domain response. For a linear time-invariant causal system, the system function h of z and the unit impulse response h of k form a one-sided z-transform pair. The nature of the poles of h of z and their distribution in the z-plane determine the form of h of k. The zeros of h of z affect the amplitude and phase of h of k, while the poles of h of z determine the form of the system response. For a causal discrete time LTI system, since h of k is a causal sequence, the region of convergence of h of z must include the point at infinity. Because the ROC cannot contain poles, it lies outside a certain circle. From the time domain definition of stability, a system must produce a bounded output for any bounded input. For a discrete time LTI system, the necessary and sufficient condition for stability is that the unit impulse response is absolutely summable. This is exactly the condition for the discrete time Fourier transform, DTFT, to exist. So the existence of the DTFT of h of k is equivalent to system stability. From the relationship between the DTFT and the z-transform, the z-transform evaluated on the unit circle equals the Fourier transform. Therefore, when the ROC of h of z includes the unit circle, the system represented by h of z is stable. Thus, the necessary and sufficient condition for stability of a discrete time LTI system is that the ROC of h of z includes the unit circle. Only when all poles of h of z lie inside the unit circle in the z-plane can the ROC include the unit circle. Therefore, for a causal discrete time LTI system, the necessary and sufficient condition for stability can be stated as: all poles of h of z lie inside the unit circle. Example 2. Given the system function h of z and the range of values of a constant a, analyze its causality and stability. First, set the denominator equal to 0 to find that the poles of h of z are a and a to the power of -1. Case 1. When the ROC is outside the magnitude of z equals a to the power of -1, the sequence is causal. The ROC does not include the unit circle, so the system is causal but unstable. Case 2. When the ROC is inside the magnitude of z equals a, the sequence is left-sided. The ROC does not include the unit circle, so the system is non-causal and unstable. Case 3. When the ROC lies between the magnitude of z equals a and the magnitude of z equals a to the power of -1, the sequence is two-sided. The ROC includes the unit circle, so the system is non-causal and stable. Finally, please reflect on today's lesson and complete the following exercises, which are designed to consolidate the knowledge points learned today and further deepen your understanding. This concludes today's class. See you in the next lesson.